The next section we look at reduction in number of states of a DFA. When we define the DFA, we said it defines a unique regular language. But a regular language can be constructed by many DFAs. So all the DFAs could be equivalent, but there could be many DFAs in construction that defines the same language. So we define a process by which we can construct a DFA with the minimum number of states. So any DFA given may have more states than required. We can combine them or compact them into a smaller equivalent DFA. So the definition that we will look at now is whether any given states, any two states are equivalent or indistinguishable, or they can be distinguished in any fashion. So we're looking to look for equivalent states so that we can combine them in any fashion. So the definition is if two states P and Q are equivalent, but means indistinguishable, that means for any string W that you're looking at, the transition ends up in an accepting state only if we end up in the same accepting state from the state Q. Then we say P and Q are equivalent or indistinguishable. So we're trying to find out two states that are equivalent or indistinguishable by constructing some sort of a procedure or a process to make them equivalent, to find out if they're equivalent. So P and Q are indistinguishable, and if Q and R also are indistinguishable, then by the same extension, P and R are also indistinguishable. So if you have established a property for P and Q and R, then the same property holds good for P and R. So all the three states are indistinguishable. So the minimization technique that we want to do to construct a minimal DFA is once again a process of construction or proof by construction. Minimization is important because the number of states of an automaton DFA has a direct effect in terms of the machine that you are trying to construct in realizing the automaton. So the smaller states, the more efficient is the machine. The minimum number of states, the more efficient is the machine. So we'll construct an equivalent DFA by looking through the DFA and combining equivalent states. The procedure used is referred to as the partitioning technique. That is, you put all of them into a mix, all the states into a mix, and try to find out if there are any equivalent states. And the technique is similar to having a group of people and then trying to see how to break them up into smaller groups, each having the same preferences. The minimization technique or the process is a constructive process. So DFA to a minimum DFA. So it's an iterative or many number of steps. So the algorithm is, to begin with, look at the machine M1 and remove any of the dead states. That is, states which are not reachable from the start state, and then remove any of the transitions because they are not defined. So a state is a dead state if it is not an accepting state and there are no outgoing transitions except to itself, and it is not connected to the given machine M1. And then divide the states, the set of states in Q into two sets. one set containing all the final states and the other set containing all the non-final states. So this is a partitioning technique. So the initial partitioning that we are doing is set of all states in one group, set of all the non-final states in a different group, and this is the partition P0. So P0 has two groups or two sets of the states of the NFA, of the DFA. So we continue as an iterative process. So the next step would be for the next partition, let's say k equal to 1. So you find out the next partition pk, which is to begin with is p1, by looking at the partition that we have so far, which is pk minus 1, and we look at all the states that are in this partition in the same group and see that if they are distinguishable in any fashion or not, or if they are equivalent in all respects. That is, if they can be distinguished by the next input, then we say they are distinguishable, and we split them into different sets in the next partition. So it is two states qi and qj are distinguishable in pk if for any input symbol a, the transitions to the next state are in different sets in the partition pk minus 1. So that means they are distinguishable on the next input. And it's an iterative process. We keep repeating this till the partition pk is finally refined enough and that there are no changes that occur in the partitioning process. So pk equal to pk minus 1, and then you stop at that, and then all states of the set in a partition, because they are equivalent, can be merged into one state. So the number of subsets of these states in the partition will be the number of states in the minimized DFA. So look at the number of sets in pk and becomes the number of states in the DFA. So this is minimal because we are grouping all equivalent states into one. So the initial state will be the state that will be the set that contains the initial state, and similarly we define the final state as a state set that contains the final state of the DFA. So as an example, so this is a DFA. Is a DFA in all respects because all transitions are uniquely defined and all transitions from every state are defined. So Q1 on a 0 is defined uniquely to Q2, Q1 on a 1 is defined to be Q5. So this is a unique example, or as an example that I can say it is a DFA, but it may not be minimal. So we apply the partitioning technique that we did before. So initially, the initial state is Q0 and the final states are Q1, Q2 and Q4. So the partitioning for P0 would be put the final states into one group, all the other states into the other group. So my initial partitioning has two sets, right? And all the states are included in the partition. That is one important thing. So you have to have all the states identified and considered for. So this is the initial partition. So the next partition is to see that if any one of these are distinguishable on the next input, any one of these are distinguishable in the next input. So we'll calculate, we'll check whether the sets in P0 can be partitioned any further. Right? So we have to take each set at a time. So start with this set and see if they can be partitioned, and then start with this set and see if they can be partitioned. So first thing is to look at Q1, Q2, Q4 and look for all the transitions defined. So if you look at the transition diagram, next overview, Q1 on a 0 and Q2 on a 0 goes to Q2, Q1 on a 1 and Q2 on a 1 goes to Q5. So the next transitions for Q1 and Q2 seems to be Q2 and Q5. But our checking process is to see if Q1 and Q2 are distinguishable on an input. So Q1 on a Q2 on a 0 are in Q2, right? And it's the same, is one state. So the Q2 of course is in the same one partition by itself anyway. So Q2 belongs to this partition, the same partition. And Q1 on a 1 and Q2 on a 1 is to Q5. So as long as they go to the same unique state, that implies that these two are not distinguishable. So they are not distinguishable. So they remain the same partition. So Q1 and Q2 for now are in the same partition as we look at the next step. So now consider maybe Q1 and Q4. Q1 on a 0, Q4 on 0 is to Q2, Q1 on a 1, Q4 on 1 to Q5. So they go to unique states, so they cannot be distinguished, right? So by the property Q1, Q2 and Q4 are not distinguishable because Q1 and Q2 are equivalent, Q1 and Q4 are equivalent. Q1, Q2 and Q4 are all in the same set, in the same partition of P1. So now look at the other set, Q0, Q3, Q5. So Q0 on a 0 is to Q3, Q3 on a 0 is to Q0, right? So we need to see if Q3 and Q0 are the same partition, which is what we started with anyway. So they are in the same partition. How about Q0 on a 1 is to Q1, Q3 on a 1 is to Q4. Okay. So Q0 and Q3 on one symbol are not distinguishable. They go to the similar equivalent states in the previous partition. So Q0 and Q3 are not distinguishable. Now try Q0 and Q5. So Q0 on a 0 is Q3, Q5 on a 0 is to Q5. Q3 and Q5 on the same partition, so it's okay. Q0 on a 1 is Q1, Q5 on a 1 is Q5. So it is goes to Q1 and Q5, which are not in the same partition. Remember, Q1 and Q5 are in different partitions. So that means Q0 and Q5 are distinguishable on the next input symbol of F1. So we have to move them out of the same partition. So Q0, Q3, Q5 has to be broken up in the next partition too. Q0 and Q3 are equivalent by the previous step, and only Q5 is not equivalent to Q0, so it becomes a step on its own, a group on its own. So the next partition now becomes, P1 becomes, we said this is equivalent, Q1, Q2, Q4, Q0, Q3 are equivalent, and Q5 is by itself in the next partition. So P0 had only, we had these two in the same group. Now we have broken up into two different groups in the partition P1. So we start the same process again for P2 to see if any further partitioning could be done from P1. So we have to start all over again from this group. So we look at Q1, Q2, Q4 and see if they are distinguishable. Obviously, by looking at the transitions Q1 and Q2 on an input 0 or 1 are not distinguishable, and similarly Q4 and Q1 are not distinguishable. As Q1 and Q4 are not distinguishable. So we look at pairs at a time to see if they are distinguishable or not. So Q1 and Q2 are not distinguishable. Q1 and Q4 are not distinguishable. So by the property, Q1, Q2, Q4 are not distinguishable. So go through, and then the next group to look at is Q0, Q3. See if they are distinguishable. And it appears in this case that they're all going to the same unique state. So they are in the same partition if they look at the states. Q0, Q3 are in the same group. Q1 and Q4 are in the same group. So Q0, Q3 are not distinguishable. When we come to the last group, Q5, a state in itself cannot be partitioned anymore, right? So once we get to one state, we do not have to worry about partitioning it. So the next partition becomes P2 is, it remains the same as P1. So P1 and P2 are the same. So this becomes the final partition. So in the partition P2, Q1 and Q2 and Q4 are all in the same group. So that means they are all equivalent and can be merged into one state. Similarly, Q0 and Q3 can be merged into one state. The initial state is any state that contains Q0, right? And the final state is any state that contains the final states, which is this state, Q1, Q2, Q4. So if you redraw and combine the merged states, Q0 and Q3 are in the same state, Q1, Q2, Q4 in the same state, and Q5 is one state. So this becomes a 3-state DFA, which is minimal. It is a minimal DFA as well as equivalent to the DFA that we started with in this example. So this DFA that we started with has 6 states, and then now we combined and partitioned them into a DFA with only 3 states. So it is a minimal DFA. So this is a constructive process, and I have many examples that you have to be able to do it easily by this partitioning technique.